In today's mini tutorial, we're going to think about the science of hemodynamics. That is the formal study of blood flow through blood vessels. And initially we're going to think about the different factors which contribute to the rate of blood flow through a vessel. So let's consider a very simple experiment. So here is a container filled with a fluid, so let's say it's water, and this fluid is up to a certain level in our container there. Now immediately we can see that there are a number of factors which govern the rate of flow of water out through the nozzle down at the bottom. In this experimental setup, one of the major determinants of flow rate, at least initially, is the amount of hydrostatic pressure which we have. That is the depth of the column of water sitting above the outlet nozzle. And clearly, if this column of water is deeper, then there will be a higher pressure. If it's smaller, there will be a lower pressure developed. So the first major determinant of the rate of flow coming from this nozzle is the amount of pressure, the pressure difference, in this case, between the hydrostatic pressure in the water and the atmospheric pressure outside of the nozzle. So number one, pressure has an important effect. The second major determinant, which I'm sure you've already gathered, is the diameter or the radius of this outlet nozzle here in the experiment. And as I'm sure you can work out for yourselves, a larger diameter outlet nozzle will lead to a faster flow rate. A smaller diameter outlet nozzle will lead to a slower flow rate. So the diameter or the radius of our outlet nozzle is the second major determinant of flow rate here. You can also imagine, and you might have experienced this firsthand, that the length of our nozzle will have an impact. So you may have experienced when using a hose pipe, very, very long hose pipes typically have much lower flow rates than much shorter hose pipes. And this is simply because of the friction between the water in the hose pipe and the wall of the pipe itself. So longer pipes provide us with lower flow rates, shorter pipes provide us with faster flow rates. So the length of our outlet nozzle or our outlet pipe is the third major determinant. Now so far all of these factors that we've considered are to do with the container or the outlet nozzle. But we mustn't forget that the properties of the liquid itself do have some bearing, and as we said, in this case it's water. But of course, you know, many different liquids have different properties, and a major property differing between different types of liquids is viscosity. Basically, how thick is the liquid. And you can imagine, say, if we had golden syrup in this experiment instead of water, the flow rate of golden syrup through that outlet nozzle would be very, very slow indeed. And that's because it has very high viscosity. If we have water, this has a much lower viscosity than syrup. And of course blood sits somewhere in between the two. Now what we were talking about previously can be quantified using this equation that's shown here. And this equation summarises what is known as Poiseuille's law. Poiseuille's law. We'll go through each of the terms in this equation individually and show how they relate to what we talked about previously. And let's quickly just add an extra I in here just to correct that spelling. So Poiseuille's law states that the flow rate, Q, is equal to pi times the pressure difference between the two ends of our pipe multiplied by the radius of the pipe to the power of 4 divided by 8 times the viscosity of the liquid, represented by this letter nu, multiplied by the length of the tube in question. Now you will notice that in this case pi over 8 is a constant, so if we're thinking about a proportionality relationship, we can remove those terms because they're not variables. And if we're thinking of our experiment using water, or in the cardiovascular system, we can remove nu, the viscosity, because that's going to be constant, that's not going to be changing. So we can convert this complicated looking equation into a more simple looking proportionality. So in this case, what we would end up with is that Q, the flow rate, is proportional to the pressure difference between the two ends of our pipe or our blood vessel, multiplied by the 4th power of the radius divided by the length. So in this case, flow rate is directly proportional to pressure difference, directly proportional to the radius to the power 4, but inversely proportional to the length. So if we increase the pressure difference, we increase the flow rate. If we increase the radius, we increase the flow rate. But if we increase the length, we decrease the flow rate. So by removing the constants, we are able to produce a simpler law of proportionality. Now, there's something in this relationship that you might find interesting or surprising, and that's this term here. The fact that flow rate is proportional to the 4th power of the radius. And this is quite remarkable, isn't it? What that basically means is that if you double the radius of a blood vessel or of a hose pipe, say, then the flow rate would increase by a factor of 16, that being 2 to the power of 4. So doubling the radius increases the flow rate by a factor of 16. And this is really, really important in the cardiovascular system, because what this means is we can control the amount of blood flowing through arteries, say, or arterioles very, very effectively, but we only need to change the diameter of them by a small amount. Additionally, if you consider, for example, diseases of arteries such as atherosclerosis that lead to blockages in arterial vessels, if we halve, so instead of doubling, if we halve the diameter of an artery due to atherosclerosis, we would decrease the amount of blood flow by a factor of 16. So diseases such as atherosclerosis or blood clots can have a very big bearing on the flow of blood through vessels. Now, one last thing to mention is that Poiseuille's law relies upon a number of assumptions. I'm going to give you a list of some of the important ones. But Poiseuille's law relies upon 4 main assumptions. Number 1, it assumes that the flow of fluid is laminar. What do we mean by laminar flow? Well, basically what you have to imagine is, if this is a tube or a blood vessel or something like that, all of the water molecules or the red blood cells are all moving in perfectly parallel pathways like this. But it goes a bit further than that, because these red cells or water molecules in the centre, in the core of the vessel, are travelling fastest, whereas the ones right out at the periphery, at the edge here, are actually not moving at all. So we've kind of got this sort of parabolic relationship almost, in terms of how fast particles are moving through those vessels. And this is a very idealistic model of fluid flow. In fact, many fluids do not pass through blood vessels in this way. They frequently pass through vessels or pipes in a turbulent manner. That is, they're not going in these parallel lines, they're kind of forming these little eddy currents like this. Okay, actually it's a lot more difficult for a fluid to flow through a pipe if it's turbulent than if it's laminar. So that's one of the assumptions of Poiseuille's law. The second assumption is that the flow is steady, i.e. it is not pulsatile. And as you're definitely aware, in the cardiovascular system this assumption does not hold, because the heart is a pulsatile pump, blood is moving in a pulsatile manner. So that assumption does not hold in the cardiovascular system. The third assumption is that the fluid that we're dealing with is a Newtonian fluid. And a Newtonian fluid is one which has a constant, unchanging viscosity. If you have a fluid which is a suspension of particles, for example blood, the viscosity here varies, and that's known as a non-Newtonian fluid. So for Poiseuille's law to hold, the fluid must be Newtonian. And finally, number 4, we must be passing through a cylindrical pipe. So this is about the most appropriate assumption in terms of the cardiovascular system, because most blood vessels are cylindrical, unless you're thinking about veins which can collapse down and take on a non-cylindrical cross-section. So when we're thinking about the cardiovascular system, really the only assumption that holds well is this one. Blood is not a Newtonian fluid, it's not got steady flow, it's pulsatile, and it's not really undergoing laminar flow. Okay, but I'll put a question mark by that because some parts will be more laminar than others. So Poiseuille's law is a very convenient law for us to model the cardiovascular system with, providing we're aware of these assumptions. But for me, the major take-home message that you need to appreciate is that small changes in vascular calibre can have massive changes in blood flow. Okay, so that's the end of this mini tutorial. Please leave some feedback if you feel that would help to improve these tutorials. Okay, thank you.